Okay, today we're gonna do beam equation or beam element. Okay. For sure, we all know what is a beam, but I'm just gonna explain to you what is a beam. So a beam is a long, slender structural member. Okay. Generally subjected to transverse loading that significant bending effects opposed to twisting or axial effects. So we'll be looking at a beam like this. Let's say we're gonna have a beam like this where we have the reaction or forces like this. Actually, let me say reaction 1 and reaction 2, and then we're gonna have a loading here. Okay, now we'll look through on how to apply finite element when solving the beam. Okay, so generally we're gonna solve a beam where we have a shear on the reaction. So we're also gonna consider this beam element. Let's say we have this, and then we're gonna have the reactions. Okay, like this. It's gonna be looking like this. Okay, and then where we're gonna have node 1 and node 2. Okay, so here we're gonna have the forces F2 and F1. Okay, and then we're gonna have the X direction and the Y direction. Okay, so here on the beam we're gonna have the moment. So we're gonna have a moment here, and we're also going to have another moment here. So we're going to say M1 and M2. So here on the moment, we're going to have a rotation. Okay, we're going to have a rotation. Let's say here we're going to have a theta 2, then here we're going to have a theta 1 for rotation. And then we're also going to have a displacement here at V. So we're going to have F1 and V1 here. Here we're going to have F2 and V2. Okay, so V1 and V2, we're gonna call them what? Displacement. V1 and V2 are what? Are displacement. And then theta 1 and theta 2, these are what? Are rotations. We call them rotations. Okay, and then what else? We have F1 and F2, which are forces, and M1 and M2 are what? Are moments, bending moments. Okay, the F1 and F2 are what? Are forces, the nodal forces. So we're gonna have node 1 here and node 2 here. Okay, and then after here, let's say we're gonna also consider this where we're gonna have a shear. Okay, we're gonna have a shear. So this one is the forces with V1 and V2 for what? For displacement. So this diagram that I'm drawing here, we're just gonna use them to derive the equation, but I'm not gonna derive the equation. I'm just gonna write the equation, the one that we're gonna use. Okay, so we're also gonna have a diagram like this. These are shear forces where we have the bending moment. So these two diagrams, the one that I draw first, that side where I show the vectors, the forces, the displacement, the rotation, the bending moment, and this one for shear force and moment. This diagram is going to help us to derive the equation, because it is going to be what? It's going to be, we're going to derive the equation using the two figures, but I'm not going to derive it. So the equation is going to be given in the exam room. So from those two diagrams, we're going to get a beam stiffness matrix. We're going to get what? A beam stiffness matrix. So we're going to have a beam stiffness matrix, which is K, the global stiffness. So it's going to be K, capital letter K, for global stiffness equals to EI over L cube. Remember, we have done this the one that has springs. Yesterday we did the bar, and then today we are doing what we call the beam. So yesterday we have the equation for the bar where it was AE over L, I think here, area multiplied by E over length. And then we have the C squared, CS, S squared. And then today we're going to do the beam stiffness where we're going to have EI over L cube, where E is modulus and I is moment of inertia and L is what? Is length. And then the equation is going to be looking like this. So we're going to have the 12, 6L, negative 12, and then 6L, like this. And then the second one is going to be 6L, 4L squared, and then negative 6L, 2L squared. Okay, and then we're going to have negative 12. This equation is going to be given in the exam or test. Okay, negative 6L, 12, negative 6L. And then the last one, we're going to have 6L, 2L squared, minus 6L, 4L squared. Okay, like this. So this is the equation that we're going to use when we are looking forward for beam stiffness matrix. This is the equation. When they say we are given a beam and then determine the global stiffness, we're going to use this equation. It's going to be given in the exam room. Okay, so the I is the moment of inertia. It's going to be also given, or you can calculate it when you are given the values. Moment of inertia, and E its modulus, L is length. Okay, L is length. We're still gonna follow everything that we did on the bar and the stiffness. So we'll have the global stiffness. After having the global stiffness, we're gonna determine the nodal displacement. Here we're gonna have the displacement and rotation. So it's gonna be a V1 and the rotation 1, V2 and rotation 2. So we're gonna be looking for displacement and rotation here on the beam. So it's V1, theta 1, V2, theta 2. Okay, the theta is rotation, V is displacement. Okay, and then after here we can determine the forces and and the moment. So if we have the global stiffness to determine the shear force and the stiffness, we're gonna use this formula. This formula. So we're gonna have the F1 M1. Remember, here we have the force and the bending moment. So it's F1 M1 and then F2 M2, all equals to the global stiffness. Our global stiffness is what? It's EI over L cube into that equation, the 12, the 6L, the negative 12, and the 6L, blah blah blah. And then we're gonna calculate what? The forces and the moment. So here we're gonna have the V1, the rotation 1, V2, rotation 2, like this. Okay, even on the side we're gonna have V1, and then we're also gonna have theta 1, V2, theta 2, like this on the other side. So this equation is gonna help us to determine the displacement. The rotation is also gonna help us to determine what? The moment and the forces. Okay, so it's still the same thing as what we were doing on the bar and stiffness. Okay, just here we have a beam. So now let's do an example to show you how to determine this beam equation using finite element. Okay, so let's say we have a beam which is fixed at one end and supported by a roller. So let's say we have a beam like this. So we're gonna do example. So let's say we're gonna have a beam which is fixed like this. And then here we're gonna have a roller, supporting roller. Okay, then let's say here we're gonna have node 1 here. We're gonna have node 1, and then here we're gonna have node 2. At node 2, we're gonna have a force of 20 kilonewton. Okay, facing down. And then here we're gonna have a supporting roller at node 3. Okay, at node 3. And then the length from node 1 to node 2 is gonna be 500 centimeter. And then from 2 to 3, it's gonna be 500 centimeter, like this. Okay, and then we'll also be given the modulus as 20 multiplied by 10 to the power of 6 Newton per centimeter. Centimeter squared. And then also gonna have the moment of inertia as 2500 centimeter to the power of 4. Okay, so here we have a beam fixed at one end here. Okay, at one end and supported by a roller. So we have a roller here at the other end, and then we have a 20 kilonewton force, or we can say loading, at the center of the beam. Okay, we have this 20 kilonewton at the center of the beam. So now they want us to determine what the global stiffness and the nodal at 2 and 3. Okay, and we're also going to determine the force at 1 and 3. Okay, so what we do first, we're going to divide this beam into two parts. So we're going to have element 1 and element 2. Okay, this is a beam. We're going to have a beam like this. This is a beam. Okay, this is a beam. So the first step here is to divide this beam into two parts. So we're gonna have to draw a free body diagram. So we're gonna have element 1 and element 2. Okay, so what we're gonna do is just to draw a free body diagram like this, where we're gonna have node 1, node 2, and node 3. Okay, node 1, node 2, node 3, and then we're gonna have what? First element and second element. We have two elements. We have element 1 and element 2. Okay, so after drawing a free body diagram, we're going to have in each node 1, node 2, node 3, we're going to have 4 factors to be considered. Okay, we're gonna have 4 factors to be considered. We're gonna have on the node 1, we're gonna have the force, we're gonna have the moment, rotation, and displacement. So this is what I'm saying. First factor is gonna be a vertical deflection or displacement, like this. So we're gonna have V1 at node 1, and then also at node 2 we're also gonna have V2. At node 3 we're also gonna have V3. Okay, and then after here we're also gonna have the forces. So we're gonna have F1 here, and then here we're gonna have F2. Remember I said each node it's supposed to have 4 factors. So now we have 2 factors. Okay, oh sorry, here is 3. Now we have 2 factors. After here we're also gonna have a bending moment. We're also gonna have a bending. So gonna have M1 with the rotation theta 1, same as node 2. We're gonna have M2 and theta 2, same as 3. We're gonna have M3 and theta 3. Okay, this is the 4 factors that I'm talking about. We have V1, F1, M1, theta 1. This is the factors that we have in our beam. Okay, and then after here we're gonna we're gonna do the global stiffness. we're going to do global stiffness because we can see now we have two elements, which means we're going to have the first global stiffness for element 1 and then the global stiffness for element 2. After that, we're going to add them and then we get the total global stiffness. Okay, so after the free body diagram, we can calculate the stiffness, the global stiffness or beam stiffness. Actually, I was supposed to say, yeah, it's the same. Beam stiffness for element 1 and element 2. So we're going to have the k to the power of 1 to show that we're dealing with what? With the first element. Okay. So it's going to be E1, I1 to show we're dealing with the first element over L1. And remember, from here to here, it's what? It's 500. Even from here to here, it's what? It's 500. Okay. And then we're going to have our equation now. So our formula is, our equation is 12, 6L, negative 12, and then 6L. And then we have 6L, 4L squared. We have a negative 6L and 2L squared. Okay, after here we're going to have a negative 12, negative 6L, 12, 6L, and then we have 6L, 2L squared minus 6L, 4L squared. There's no need to cram this formula, it's going to be given. And then here we're going to have a V1, a theta 1, V2, and theta 2. Okay, so this we call them the slope or nodal deflection or deformation, the rotation and displacement. Okay, after here we can substitute our length, we can substitute our values. We have the E is 20 times 10 to the power of 6, and then I is 2.5, the L, this is to the power of 3, and the L for element 1 is what? It's 500. Okay, and then now we have the value of L. L is going to be 500, so it's going to be 12, 6 times 500, negative 12, 6 times 500, so we're just going to substitute the values that we have here, and then we get what? The first element stiffness. So it's going to be K to the power of 1.
Yes, sir. The value of the modulus, so it's in kilometers squared, right? So do we have to convert everything to meters since that one is in kilometers squared?
Oh, sorry, let me go back. Okay, our modulus is in Newton per centimeter square. Sorry, it's Newton.
Oh, okay.
Yeah.
So we give everything in centimeters.
Yes. So there's no need to convert anything. So they are both in centimeters.
All right.
Okay. So now K, the first element is going to be K to the power of 1, or equals to the E. E, it's 20 multiplied by 10 to the power of 6, and then I is 2.5, all over 500 to the power of 3, okay, into, so we're going to substitute the values of L here. So we're going to have 12 here, and then it's going to be 6. It's going to be 6 multiplied by 500 minus 12, 6 multiplied by 500. So it's going to be 6 times 500, which is going to be 3,000. So everywhere there's L, we're going to substitute with the 500. Okay, and then we're going to have this 20 times 10 to the power of 6 times 2.5 over 500 to the power of 3 into, I'm going to write them here. So we're going to have 12, 3,000, and then we're going to have minus 12, and then 3,000. The second row is going to be 3,000. It's 6 multiplied by L, and then the second one is 4L squared, so it's going to be 4 multiplied by 500 to the power of 2, which is going to be 1, times 10 to the power of 6, which is 1 million. Okay, and then the third one is going to be negative 6 multiplied by 500, which is going to be what? A negative 3,000. And the last one is going to be a 2L squared. 2L squared is going to be 5 multiplied by 10 to the power of 5. Okay, like this. The third one is going to be minus 12, minus 3,000. Okay, and then 12, then 3,000. The last one is going to be 3,000. And then 5 multiplied by 10 to the power of 5. Then minus 3,000. Then here 1 times 10 to the power of 6, like this. Okay, and then on top we're gonna have V1, theta 1, V2, and then theta 2, like this. So this is our first element, and then second element we're still gonna do the same, where we're going to have the k to the power of 2 to show that we're doing the second element. So it's gonna be E2I2 over L2 cube. The reason why I'm writing 2, sometimes you'll be given each element will have its modulus and moment of inertia, but here we are given moment of inertia and modulus as 20 times 10 to the power of 6 and 2.5. Okay, and then here we're going to have that formula, which is 12 6L minus 12 6L. Okay, you're just gonna copy the formula and then substitute. Since we have the same thing, the length is 500, the E is 20 times 10 to the power of 6, and the I is 2.5. The K2 is gonna be equals to K1. Okay, we're gonna have the same thing, but let me just write it. So for us to get the total of the total of stiffness, so K2 is gonna be the 20 times 10 to the power of 6, 2.5, and then 500 all to the power of 3 into, it's gonna be 12, 3,000 minus 12, and then 3,000. Okay, and then we have 3,000. Still gonna be the same as K1. The 1 multiplied by 10 to the power of 6, and then minus 3,000. Then we have 5 times 10 to the power of 5. Okay, and then minus 12, minus 3,000. And then 12 minus 3,000. And then the last one is going to be 3,000. Then the 5 times 10 to the power of 5. Then minus 3,000. And then 1 times 10 to the power of 6. Okay, here since it's element 2, we're going to have V2 theta 2 and then V3 theta 3. Okay, it's for element 2. Element 2 is from node 2 to node 3. That's why we have V2, theta 2, V3, theta 3. So. And then for the global stiffness, we're gonna add the two elements. We're gonna add element 1 plus element 2. Okay, so we're going to have this K1 plus K2, and then we're gonna have 20 times 10 to the power of 6 multiplied by 2.5 over 500. It's gonna be 400 into, and then here we're going to check V1, V2, V3, V4, theta 1, theta 2, theta 3. So since we have 3 nodes, which means we're going to have 6 by 6 matrix. So we're gonna have V1, theta 1, V2, theta 2, and then V3, theta 3. 2, 4, 6. Yes, as I said, we're gonna have a 6 by 6 matrix. And then what we're going to do, we're going to check, okay, which one, we're gonna check V1 and V1 and then get the value. V1 and theta 1, we get the value. So V1 and V2, we get the value. So when we check V1 and V1, we're gonna have 12. V1 and theta 1, we're gonna have a 3000. Okay, and then V2, we're gonna have a negative 12, V1 and V2. And then for theta 2, V1 and theta 2 is gonna be 3000. And then V1 and V3, we don't have V1 and V3, so it's gonna be 0, 0. V1 and theta 3 we don't have, so it's 0. And then after that, we're gonna come to theta 1. And then we're gonna check theta 1 and V1. Theta 1 and V1 is 3000. Okay, and then theta 1 and theta 1. Theta 1 and theta 1, it's 1 times 10 times 1 times 10 to the power of 6. And then theta 1 and V2. Theta 1 and V2, we're gonna get a negative 3000. And then theta 1 and theta 2. Theta 1 and theta 2, it's 5 multiplied by 10 to the power of 5. And then theta 1 and V3. Theta 1 and V3, we don't have theta 1 and V3. Okay, and then after here, we're gonna come to what? To V2, then theta 2, V3, and then theta 3. Okay, guys, this is the same as what we did on bar element and the stiffness element. Okay, so here, after here, we're gonna do the V2, which is going to be a negative 12, negative 3K, 24, because we're going to have 2 V2. We have V2 on K2, and then we also have V2 and V2 on K1. So we're going to add the 2, where we'll have what? 24. It's going to be 12 plus 12, 24, and then here it's going to be 0, negative 12, and then 3K. And then theta 2, on theta 2, we're going to have a 3000. Theta 2, we're going to have a 3000, and then 5 times 10 to the power 5, and then we're going to have 0. Then we're going to have theta 2 and theta 2 on both K1 and K2, so it's going to be 2 times 10 to the power of 6. And then here we're going to have a negative 3K, and then here we're going to have a 6 times 10 to the power of 5 on theta 2 and theta 3. It's 5, not 6. 5 times 10 to the power of 6 here. And then on V3, we're going to have 0, 0, and then negative 12, and negative 3000. And here we're going to have the 5 times 10 to the power of 6 times 10 to the power of 5. I'm sorry, guys. It's not 6, it's 5. Here, and then the last one, we're going to have the negative 3K, And then for theta 3, we're also going to have 0, 0 here, and then a 3000 and a 5 times 10 to the power 5. And then here we're going to have a negative 3000. And then the last one is going to be a 1 multiplied by 10 to the power of 6. Okay, like this. So this is how we determine the stiffness. We're going to have element 1 plus element 2. Sometimes you'll be given 3 elements, so we're going to have plus k to the power of 3 if we have 3 elements. Okay, so now we have what we have the global stiffness. After determining the global stiffness, they'll ask us to determine what the displacement and rotation. So we have to determine the displacement and rotation for what? For V2 and theta 3. So number 2, we're going to determine theta 3, theta 2, and V2. We're looking for this. We're going to look for this. So to look for this, we have to apply the boundary condition. So we have to apply the boundary condition. Let's go back a bit and check the boundary conditions. So from our example here, we were given a fixed point like this, a bar, a beam like this, where we have the roller and we have the force here, and then we have node 1, node 2, and node 3. Okay, node 1, node 2, and node 3. So here we're going to have the V1 and M1, F1, and theta 1. Same as 2, we're going to have V2, M2, F2, theta 2, same as 3. So since node 1 is fixed, which means our F1, this is a boundary condition. We check boundary condition from the diagram. So which means F1 is going to be equals to 0, and then F1 is going to be equals to 0, and then no, I'm lying. Supposed to be V1. V1 is going to be equals to 0, and the theta 1 is going to be equals to 0 because what? It's fixed, because node 1 is what? It's fixed. Yeah, I think even F1 is also 0 because it's fixed. And then on node 2, we were given 20 kilonewton here. 20 kilonewton. So on F2, we have what? F2 is equals to, is going to be a negative 20 because it's facing down. Okay, and then here, since we have the force, and then we're going to be looking, we're going to have a value for what? For theta 2. That's what we're going to look for, and V2. We're going to look for theta 2 and V2. And then here on the rotation, on the roller supporting, there is a moment on the horizontal, like on this side, we have the moment, okay? And then on the vertical, we don't have moment. On the vertical, we don't have moment, which means the V3 here, V3 is going to be 0 because we don't have a moment on what? On a vertical. And then we're going to have the theta 3. So theta 3 is going to have the value. So we're going to look for theta 2, V2, and theta 3. Okay. So this is what we're going to look here. We were checking the boundary condition. So we're going to look for this. So we're going to look for this theta 2, theta 3, and V3. So our boundary condition, V1 is equals to 0, theta 1 is equals to 0, and then also V3 is equals to 0 because there's no moment in a vertical direction. Okay, so we have V1 is equals to 0, theta 1 is equals to 0, V3 is equals to 0, and also the bending moment at node 2, M2 is also going to be equals to 0, and M3 is also going to be equals to 0. Okay. Okay, yes, M2, M3 is also going to be equals to 0. So what we're going to do, we're going to do the forces. So it's going to be F1, M1, F2, M2, and then F3, M3. All equals to what? To the global stiffness, So it's going to be 400 into the values that we calculated. Okay, here. And then after writing the values, remember we had a V1, theta 1, V2, theta 2, V3, and then theta 3, like this. So now we have V1 is 0, so wherever there's V1 we're gonna cancel, okay, and wherever the theta 1 we're also gonna cancel those values, and then we'll cancel the values, and then we're looking for V2, theta 2, and then V3 is also 0, so wherever there's V3 we're gonna cancel, and then we're gonna left with theta 3. So this is what I'm saying. So this is what I'm saying. V1 is equals to 0, so we're going to cancel it like this, wherever there's V1. And then theta 1 is also equals to 0, so we're going to cancel it. So V1 and V1, theta 1 and theta 1, we're going to cancel. And also V3 is equals to 0. It's V3 here. So we're gonna left with V2, theta 2, theta 3, and V2, theta 2, and theta 3. So we're gonna left with that. Okay, so we're going to have the we're gonna have F2 and M2 and M3. Okay, all equals to 400 into, so here we're gonna have the V2, the theta 2, and theta 3. Okay, so which is gonna be what? A 24, 0, and what? And 3000 for theta 3. Okay, and 3000. And also we're gonna have what? For M2 we're gonna have the 0, 2 times 10 to the power of 6, and then 5 times 10 to the power of 5, and then we're also gonna have for M3 we're going to have 3000, and then 5 times 10 to the power of 5, and then we have 10 to the power of 6 here. Okay, so from here we can calculate the V2 and theta 2. So here it's F2. We were given F2 as what? As 20 kilonewton. So what we're going to do here, we're going to solve for V2, theta 2, and theta 3. Okay, so it's gonna be F2 equals to 400 into 24V2, then plus 0 theta 2 plus 3000 theta 3, like this. And then M2 is going to be 400 into 0V2 plus 2 times 10 to the power of 6 theta 2. Here we just want to calculate the theta 2 and the V2, okay? Then plus 5 times 10 to the power of 5 theta 3. And then for M3, it's equals to 400 into, it's going to be 3000 V2 plus 5 times 5 to the power of 5 times 10 to the power of 5 theta 2 plus 10 to the power of 6 theta 3. So 1 times 10 to the power of 6. And after here, we're going to substitute the value of F2, which is a negative 20 kilonewton. And then M2 is equals to 0, M3 is equals to 0. And then now we can use what we call simultaneous equation and then solve for theta 2, theta 3, and V2. Okay, V2, theta 2, and theta 3. We're looking for that. So here we can use simultaneous equation to determine that. Okay, so and then we'll be done with this equation. We'll not be done. So after calculating the V2, theta 2, and theta 3, we're gonna come back and calculate the forces. So the next question they will ask us to determine what? To determine the forces. So you're gonna determine F1 and they can say F1 and F2 or F2 we have. They can say determine F1 and F3. So to determine F1 and F3, so it's gonna be F1 equals to 400 into, it's gonna be 12 times V1, 3000 times theta 1, negative 12 times V2, 3000 times theta 2. So and then you're gonna get what? You're gonna get the value of what? Of F1. So this is what I'm saying. To determine F1, it's gonna be 400. Just gonna go back to your the global stiffness equation. So it's gonna be 400 into 12 V1 and then plus 3000 theta 1, okay, and then minus 12 V2 plus 3000 theta 2, okay, and then plus 0 V3 plus 0 theta 3. And then remember we'll be calculated the value of V2, theta 2, and theta 3. And then our V1 and theta 1 and V3 is equals to 0. And then we'll be calculated V2 and theta 2 and theta 3. You're just going to substitute the values and then you get what? Your force. And you get your force. Okay, this is what you do under beam. The first thing, you have to draw a free body diagram and then divide that beam into 2. If we have 4 nodes, we're gonna have 3 elements. So depending on the nodes that we have, and then you're gonna divide the beam into according to the nodes that we have. Okay, and then for the last part that we're gonna do here under beam, I'm gonna show you when we have a UDL. Remember the beam that we were doing, it didn't have a UDL. So we're not talking about the UDL. Let's say we have a beam like this. We have a beam which is fixed on both ends. Okay, it's fixed on both ends, and then we have node 1 here, and then we have node 2, then here we have node 3. Okay, between node 2 and node 3 we have a UDL. I hope you all know what is UDL. So we have a UDL like this. Okay, and then from 1 to 2 we have a length which is 1 meter, and then from 2 to 3 we also have a length which is 1 meter. And then here the UDL we have it as 24 kilonewton per meter. Okay, and the E were given as 200 gigapascal, and then the moment of inertia were given as 1 times 10 to the power of 6 meter to the power of 4. Okay, like this. We are given it like this. So what we're going to do here, we're also going to divide this beam into 2 because we have what? We have 3 nodes. So we're going to have element 1 and element 2. Element 2, it has what? It has a UDL. It has a UDL. So what we're going to do, we're going to divide this into 2. Just draw a free body diagram here. Okay. So we're going to have 1, 2, 3, and then we have a 1 meter in between. 1 meter and 1 meter. Okay, so remember, every time when we draw a free body diagram, we're going to have 4 factors, which is displacement, force, rotation, and moment. Okay, so we're gonna have the moment 1, and then here we're gonna have M2, then here we're gonna have M3. So we're also gonna have F3, V3, and then we're also gonna have a theta 3. Okay, same as 2 and 1. So we're gonna have F1, a theta 1, and V1. Here we're gonna have a V2, F2, and what? And the theta 2 for rotation. Okay, so you draw your free body diagram, and then since here we have a UDL, we're gonna separate it on the side. So we're gonna have something like this for the UDL. So it's gonna be 2 and 3. So for UDL, the moment is gonna be, the other one's gonna move clockwise, the other one is gonna move anti-clockwise. Anti-clockwise. So we're gonna have this and this for what? For UDL. For UDL, okay? And then after here, we can do the stiffness, the beam stiffness. So we're gonna have the K1 for element 1, which is gonna be equals to E1 I1 over the length 1 cube into our formula, the 12, the 6L, the negative 12, 6L, and then we write that formula. And then also on K2, we're still gonna have the same E2 I2 over L2 cube, and then we're gonna have that formula. And after here, you're gonna substitute the values, okay, and then get the global stiffness like this. Okay, after global stiffness, remember, we're gonna do what? The F is equals to the global stiffness, this one, F equals to the global stiffness multiplied by what? By the displacement and rotation. Okay, so we're gonna have something like this. But since we have a UDL, remember, we were not given the force, we were not given the moment. Most of the time we will be given, or okay, we have the force here is 20 kilonewton, but here we were given what? A UDL, which is what? 24 kilonewton per meter. 24 kilonewton per meter. So this one is W. Sorry, is W equals to 24. Okay, so when it comes to calculating the nodal displacement and rotation, remember we use this equation. So we're gonna have the F1, M1, F2, M2, and then F3 and M3, all equals to the global stiffness. Okay, multiply by what? It's gonna be what? A V1, the theta 1, V2, theta 2, V3, and theta 3. Okay, so remember, we don't have the force, we don't have the moment, we have the UDL, which is 24. We have a UDL which is 24 kilonewton per meter. So how are we going to use this 24 kilonewton per meter to get what? To get the force and the moment. So we're gonna use this formula. So to calculate the force when we're given the UDL, it's what? It's F equals to the UDL multiplied by L over 2, okay? Over 2. So it's to calculate the force. It's UDL multiplied by length over 2. So this L is going to be for the 1, L1, which is 1 meter. And then to calculate the moment, moment is going to be equals to UDL multiplied by L squared, okay? Over, actually I'm not supposed to write 1 here, it's just L, okay? Yeah, for F1. Okay, M3 is equals to UDL squared over what? Over 12. Over 12. So to calculate force, we use this formula. And then to calculate moment, we use this formula. UDL multiplied by L squared over 12, okay? And then you're going to get the value of F1, M1, F2, M2, and F3. But since here, the UDL, it's between 2 and 3. So which means here at 1 and 3, the F is going to be equals to 0 because it's what? It's fixed. Also, and F3 here is going to be equals to what? It's going to be equals to 0 because it's fixed. So we're going to get F2 and M2 using that formula. So here we'll be looking for what? For F2. And then we're also going to be looking for what? For M2. So since F1, actually I was supposed to write it here but it's fine. So since node 1, it's fixed, which means the force is going to be equals to 0, even the moment is going to be equals to 0. And then F2 is equals to what? UDL multiplied by L over 2. And then moment 2 is going to be what? UDL L squared over what? Over 12. And then you get your answer. So the W is what? Is equals to 24. Just going to substitute. And then F3 is equals to 0 because it's fixed. And also M3 is equals to what? Is equals to 0 because what? It's fixed. So we're going to stop here. And then, yeah, we're going to stop here. That's what you have to know under the beam equation. So when we're given the UDL, just have to use these formulas for the force, and then for the moment. For the force is double L over 2, and then for moment is double L squared over 12. Okay, yeah, we're gonna stop here, and then after here you just have to calculate what the displacement and rotation, and after calculating the displacement and rotation, you're gonna calculate the forces F1 and F2.
All right. Tazama question on TFAZT.
Yeah.
So most calculate K1 yashna K2 let's say it ashna aitashwa zifanti. If it global stiffness parapasi the add or what the add multiplier.
Uko do multiplier hey noni na 12 hey noni na 6 times.
Let's say E1 it.
K1.
E1 na E1.
Okay.
E1 na I1 just azilinga na E2 na I2 me different na. So let's say you have number 1 corner 400 and number 2 corner 200. Nichumwa the global stiffness into like the overall K1 plus K2.
Okay, uko do multiply 400 by 12, 400 by 6L, 400 by negative 12. And then here, udo multiply 200 by 12, 200 by 6L. Udo multiply zote zirenga panga ngomu nga 400, and then zote zirenga ngomu nga 200. Udo kono ze combine ashipezi, udo kono ze eda mapezi serone ashikono wana mini V1, theta 1, V2, theta 2. So araziko fano to jasa common factor ngwala 400. This a fano udo timesa atimesa.
All right, okay, and more. Thank you.
Okay, Anna says, yeah, we're gonna stop here. Thanks. Bye bye.